Welcome to this module, where we explore the integration of decentralized and distributed renewable energy systems, or DRE systems, into existing electrical grids. As the world transitions toward clean and sustainable energy, renewable sources like solar and wind are key to reducing emissions and enhancing energy security. In this session, we'll understand how DRE technologies, which generate power locally, can be effectively connected to the grid while maintaining efficiency, reliability, and safety. We'll also gain insights into key principles, challenges, and best practices for grid integration, helping shape a more resilient and sustainable energy future. Distributed renewable energy, or DRE, sources like solar and wind are the backbone of modern sustainable power systems. When integrated into grids operated by power distribution companies, they help create a cleaner, more decentralized, and resilient energy future. By connecting rooftop solar and other local power sources directly to the grid, we move from a one-way flow of electricity to a two-way interactive system where consumers can also become producers. This transformation brings huge benefits in efficiency, reliability, and energy access, but it also introduces new technical and regulatory challenges. To overcome these, we need smart grid technologies and modern infrastructure that can support the next generation of renewable energy integration. Definition of DRE: localized renewable energy generation, where a solar PV system generates electricity and injects either into an isolated and independent mini-grid or into the existing state grid. Grid-tied DRE systems allow a bidirectional flow of energy. Key components like DC to AC inverter and smart/bidirectional meter, etc. And standards facilitate this process safely and efficiently. DC to AC inverter: solar panels produce direct current DC, which an inverter converts into the alternating current AC used by the electrical grid. The inverter is crucial for matching the grid's specific frequency, voltage, and phase. Smart/bidirectional meter: this device measures both the electricity consumed from the grid and the surplus power a solar system feed back into it. This is essential for net metering programs, where solar owners receive credits for the excess energy they generate. A suitable commercial arrangement is developed between the consumer and the grid for the payment against the net consumption depending upon the category of the consumer. Importance of solar PV in distributed generation: enhanced grid resilience and reliability. A decentralized network of solar installations reduces dependence on a few large power plants, strengthening the grid against failures from extreme weather or other disruptions. Microgrids with solar can operate independently during a main grid failure. Reduced transmission losses: by generating electricity closer to where it is consumed, DRE systems reduce the amount of energy lost during long-distance transmission. In some regions, these losses can be significant. Lower electricity costs: DRE can reduce overall electricity costs for consumers by offsetting purchases from the utility and selling excess power back to the grid. For utilities, distributed generation can lower demand peaks, delaying the need for expensive infrastructure upgrades. Environmental sustainability: integrating more solar power significantly reduces reliance on fossil fuels, lowering greenhouse gas emissions and pollution. Role of grid integration in balancing demand and supply: maintaining equilibrium on the electrical grid is critical because electricity must be consumed the moment it is generated. Without proper grid integration, a mismatch between supply and demand can cause system frequency and voltage fluctuations, leading to grid instability and potential blackouts. Integrating DRE with the existing grid ensures optimal utilization of renewable energy, reduces losses, and enhances energy access. It also supports national goals for carbon neutrality and energy security. Reduces dependency on fossil fuels. By displacing fossil fuel-based generation, DRE improves local air quality, which can reduce the incidence of respiratory and cardiovascular diseases associated with burning fossil fuels. Certain DRE technologies, such as those using biomass, efficiently manage organic waste by converting it into electricity, improves grid resilience and reliability, supports rural electrification, improving quality of life of rural consumers significantly through decentralized generation, enables environmentally cleaner and more sustainable energy mix. Grid integration requires strict adherence to international and national standards, such as IEEE 1547 and IEEE 519, to ensure safety and performance. These define limits on voltage, frequency, harmonics, and synchronization for reliable grid operations. IEEE 1547, Guidelines for Interconnecting Distributed Resources, defining the technical requirements for connecting DRE to the grid. IEEE 519, Harmonic Control Standards for Clean Power. This standard stipulates the interconnection of DRE sources, such as PV systems, with the grid. Voltage range: 80 to 110%. Power factor is greater than or equal to 0.9 lagging. Protection systems: anti-islanding, overload, and disconnecting protocols. These standards ensure safety, power quality, and the reliable operation of the grid. Strict adherence to these specifications is crucial to prevent grid instability and ensure safe operations. Before connecting DRE systems to the grid, rigorous testing ensures compliance, reliability, and safety. This includes pre-commissioning checks, inverter synchronization, and anti-islanding functionality verification. Component testing before, during, and after installation. Pre-commissioning inspection for layout and capacity compliance. Synchronization testing, matching voltage, frequency, and phase. Performance and SCADA monitoring system validation. Anti-islanding protection is a safety feature in grid-tied distributed energy systems like solar that automatically shuts down the system when the main utility grid goes down to prevent it from continuing to power an isolated island of the grid. This is crucial for protecting utility workers from electrocution and preventing damage to grid equipment during power outages. Despite its benefits, integrating DRE presents challenges like grid instability, phase imbalance, and harmonics. High DRE penetration may strain infrastructure and protection systems. The integration of DRE is complex and requires innovative solutions to address several key issues. Voltage fluctuations and frequency instability. Solar power generation fluctuates depending on weather and time of day. This variability must be managed to maintain a stable balance between supply and demand. As a solution, battery energy storage systems (BEES) can store excess solar power and release it when generation is low to meet the demand. Reverse power flow during low demand periods. Phase imbalance and harmonics distortion. Safety and coordination issues for maintenance crews. Grid infrastructure limitations. Most traditional grids were designed for one-way power flow from centralized plants. High levels of DRE create new challenges for bidirectional power flow, voltage regulation, and grid management. As a solution, smart grid technologies use real-time monitoring and advanced analytics to optimize energy flow and manage power quality. Modernizing transmission and distribution lines is necessary to handle increased renewable capacity. Anti-islanding protection. This critical safety feature automatically disconnects the solar system from the grid during a power outage. It prevents dangerous backfeeding of power to the grid, which could injure utility workers performing repairs. Cybersecurity threats. As grids become more digitized with smart meters and monitoring, they become more vulnerable to cyber attacks. Microgrids and blockchain-based energy trading can enhance grid security by isolating vulnerabilities and decentralizing control. To mitigate challenges, utilities and developers must adopt technological, procedural, and regulatory measures for reliable grid operation. Deploy multi-stage inverters with L/C harmonic filters. Enable LVRT, HVRT capabilities for grid stability. Implement smart grid monitoring and micro-balancing zones. Promote even distribution of solar plants across feeders. DRE integration supports global climate goals by reducing carbon emissions and creating local economic opportunities. It also minimizes transmission losses and provides energy access to remote areas, carbon dioxide emission reduction, and improved air quality. Energy cost stabilization through local generation, job creation in renewable energy sectors, enhanced efficiency, and reduced transmission losses. Safety is paramount during installation, operation, and maintenance of grid-connected DRE systems. Compliance with local regulations ensures personnel safety and grid reliability. Proper earthing and lightning protection systems. Isolation switches for DC and AC sides. Certified metering and anti-islanding mechanisms. Adherence to local grid codes and safety standards. Globally, countries like India, Germany, and Japan have achieved successful DRE integration through policy support, advanced technologies, and smart grid innovation. India, rooftop solar mission and net metering success. Germany, energy transition through distributed renewables. Japan, smart city models using solar microgrids. Positive outcomes, reliability, cost savings, and emissions reduction. The next decade will witness AI-driven energy management, hybrid renewable systems, and digitalized smart grids that self-optimize for reliability and efficiency. AI-based predictive grid balancing systems. Integration of solar with wind and energy storage. Blockchain-enabled energy trading models shift toward decentralized smart microgrids. Integrating solar PV-based DRE systems into the grid is key to a sustainable future. With strong technical compliance, robust safety measures, and innovative policies, the world can achieve a cleaner, more resilient energy ecosystem. Grid integration maximizes renewable utilization. Standards ensure safety and quality. Testing and monitoring guarantee performance. Future belongs to digital, decentralized energy systems. Thanks for going through and reading. Don't forget to like, share, and subscribe for more solar insights from I-SED Academy. Please go to I-SED Academy platform for detailed learning about solar technologies.